Welcome to Chapter 26, The Properties of Light. In this chapter, we will talk about electromagnetic waves, the electromagnetic spectrum, transparent material, opaque materials, and the eye. Light is the only thing we can see. It originates from the accelerated motion of electrons. It is an electromagnetic phenomenon. That's the reason we call it electromagnetic. And it is a wave. That's, of course, why we call it an electromagnetic wave. Now, light is not the only electromagnetic wave we can sense. We can actually sense infrared. We have special receptors in our skin, and because we can sense infrared, that protects us from getting burned. Now, to make an electromagnetic wave, basically all you do is wiggle a charge. Electric charge has an electric field that surrounds it. If you wiggle the charge up and down, it will be accelerated, and the E field will increase and decrease in the same direction at the same rate. So a changing electric field will induce and generate a changing magnetic field, and the changing magnetic field generates a changing electric field. Induces a changing electric field will induce a changing magnetic field, and so on and so forth. Now, the changing electric and magnetic fields generate an electromagnetic wave. The wave speed is 3 times 10 to the 8th meters per second in vacuum. If the wave carries energy at this certain speed, the system does not violate the laws of conservation of energy and also does not die out. One half of the total energy is carried in the electric field, the other half is in the magnetic field. The electric field is perpendicular to the magnetic field, and both the electric and magnetic fields are perpendicular to the direction of the waves travel. So in other words, if the electric field is vibrating vertically, the magnetic field will be vibrating horizontally, and the direction of travel of the wave will be perpendicular to both the electric and magnetic fields. They also rise and fall at the same times. They are in phase with each other, and they also have the same frequency and the same wavelength as each other. Electromagnetic waves are produced by a vibrating electric charge. They are transverse waves. They travel through the vacuum at the velocity of 3 times 10 to the 8 meters per second, and that is, of course, the speed of light. So electromagnetic waves are made up of vibrating electric and magnetic fields. A changing electric field, which is created by a wiggling electric charge, induces a changing magnetic field, which induces a changing electric field, etc., etc. If either one of the waves is collapsed or wiped out, the other one disappears. You have to have both waves. If an electron vibrates up and down 1,000 times each second, it generates an electromagnetic wave width. Now, 1,000 times per second is 1,000 hertz. So none of these answers are correct. So a vibrating electron would emit a wave with a frequency of 1,000 hertz, which is not in the list above. So none of the above is the correct answer. Read things carefully. Okay, an electromagnetic spectrum is basically the classification of electromagnetic waves according to frequency or wavelength, or energy, whichever one you want to relate it to, because they're all related to each other. The lowest frequency of light that we can see appears red. The highest frequency of light that we can see appears violet. Higher the frequency than that would be ultraviolet, and that's more energy and can cause sunburn. Beyond that are X-rays and gamma rays, which are even more damaging to human cells. There is no sharp boundary between regions, and there are no upper or lower boundary on the electromagnetic spectrum. Here's a picture of the electromagnetic spectrum, rather it's a diagram, and note the visible light one. This actually is, on this picture to this scale, you couldn't even see that. Okay, we just expanded this just for convenience. In reality, it's the narrowest part of the electromagnetic spectrum. Now, at this end, to the left, that is the low frequency. Frequencies at the bottom here. That's a low frequency, long wavelength, lowest energy part of the electromagnetic spectrum. The energy is the energy per photon. Photon is a packet of energy in the light. And notice the wall outlet, that 120 volts, 60 hertz, that's a frequency. That is an electromagnetic wave. That's way down here. The wavelength of that is well over 3 times 10 to the 6th meters. So you can imagine how long that wave is. That's one wavelength. Now, as you go further and further to the right here, the frequency gets higher and higher. You can see that on this bottom chart. The wavelength gets shorter and shorter, and the energy per photon increases. Also, so does the potential for damage to human cells. So here at this end here, this is the radio wave end. Notice how these things all overlap. In some places, they completely overlap. That's because there's no real perfect delineation here. There's no agreement on where the infrared ends and radio waves begin. And microwaves are really just a form of radio waves. This is where your old-fashioned AM radio wave are, your old-fashioned TV, FM radio. Microwaves, your microwave oven, cell phone, that kind of stuff. Wi-Fi connections are all microwaves. Infrared is what we think of as heat. We do have sensors for infrared in our skin to protect us from getting burned. And that's what you feel when you hold your hand near a hot object, but not quite touching it. You can kind of feel that energy on the palm of your hand. Visible light spectrum runs from about 700 nanometers at red down to about 400 nanometers of violet. And there's no real sharp, just like for the rest of this, there's no real sharp edge here. Nobody really agrees 100% is what. And some people can actually see into the near infrared, and some people can actually see into the near UV. I can actually see UV to a certain extent. It isn't like a sharp edge. Now, if you get above violet, you get into ultraviolet. This is where cell damage starts to occur. The energy of this light is high enough to damage your cells, potentially. This is why you want to be wearing sunglasses and sunscreen. If you get further than that, you get x-rays. X-rays can penetrate your tissues. That's the reason we use them to take x-rays of broken bones and your teeth, because they can actually penetrate tissues. If they can penetrate your tissues and they're this energetic, they can also damage them if you get enough of them. If you get further than that, you get gamma rays, and those are a lot more dangerous. Visible light waves are actually a very small part of the electromagnetic spectrum. Radio waves, microwaves, infrared waves, ultraviolet rays, X-rays, and gamma rays are all electromagnetic waves. They all travel at a velocity of 3 times 10 to the 8 meters per second in vacuum. Radio waves are low energy, low frequency, long wavelength electromagnetic waves. Gamma rays are high energy, high frequency, short wavelength electromagnetic waves. Other waves are intermediate in energy, frequency, and wavelength. And I would strongly suggest that you take this slide and copy this or something like this into your notebook. There's probably one available in your book too. The electromagnetic spectrum spans waves ranging from the lowest to the highest frequency. The smallest portion of electromagnetic spectrum is that of visible light. Which of these is fundamentally different from the others? Sound waves. The old expression that they can't hear you scream in space. Well, sound wave is a matter wave. Okay, it requires a medium in which to transfer. Space does not have any air, so there's no way for space to transmit sound waves because there's no medium there. But electromagnetic radiation travels through vacuum of space much better than it does through anything else. So they can see you scream in space, but they can't hear you scream in space. That's the way I like to remind students of the difference between electromagnetic waves, which can travel through a vacuum, and other ways which cannot. Now, light is actually sort of created similarly due to sound. Both are due to vibrations, due to a vibrating source. For sound, it's usually something mechanical that's vibrating, like a tuning fork or a rubber band that you pluck. For electromagnetic waves, it would be electrons, moving charges that are vibrating back and forth. Now, how does light travel through a transparent material such as glass? Well, all materials are mostly empty space. They're good vacuums to 1 part in 10 to the 15th. They're 99.9 with about 13.9% empty space. So most of the time, the light is traveling at the speed of light, 3 times 10 to the 8 meters per second, the speed of light in vacuum. But there are atoms inside the transparent material, and the light wave can encounter the electrons in these atoms and energize them. And what happens is what they do is they transfer their energy to the electrons, and the electrons vibrate more. But eventually, the electrons give up their energy and then re-emit the light photon. It's actually another photon, and then it travels and maybe will encounter another atom, which sort of gobbles it up and becomes more energized. The electrons of that become more energized, but eventually they give up that energy, emit another photon, and the thing keeps going. Light always travels at the speed of light in the empty space between the atoms because it's a vacuum. When it encounters an atom, it is absorbed and then re-emitted. This process takes time, lowering the effective speed. It's like making repeated pit stops on a road trip. You might travel 70 miles an hour on the highway, but each pit stop takes time, making your travel time longer and your effective speed lower. Electrons or molecules in the glass are forced into vibration. The energy is momentarily absorbed and vibrates the electrons in the glass. This vibrating electron either emits a photon, which is a little body of light, sort of a light energy packet, or it transfers the energy as heat. The time delay between the absorption and re-emission of energy of the vibrating electrons results in a lower average speed of light through the transparent material. Now, in glass, infrared waves, which have frequencies lower than that of visible light, cause not only the electrons, but the entire atoms or molecules to vibrate. This increases the temperature of the material. And you felt that if you put something under a heat lamp produces a lot of infrared energy. If you put something under a heat lamp, it warms up. So we see that Glass is transparent to visible light, but is not transparent to ultraviolet or infrared light. The average speed of light through different materials in vacuum, it is the speed of light in vacuum, which is 3 times 10 to the 8 meters per second. In atmosphere, it will be slightly less than C. It's like less than 0.1% slower in atmosphere than it is with vacuum. But in this class, we usually ignore that tiny difference and we just round it off to C. In water, it's about 3/4 of what it is in vacuum. In glass, is only 2/3 of what it is in vacuum. That somewhat depends upon the material. In diamond, it's about 40% of what it is in vacuum. Strictly speaking, the photons of light incident on glass are not the ones that travel through and exit the other side. Instead, they've been absorbed and re-emitted and absorbed and re-emitted many times. So strictly speaking, they're not exactly the same ones. They'll be their twins, but they're not the same ones. Compared with the frequency of illuminating light on the sheet of transparent plastic, the frequency of light that is transmitted is the same. The frequency is the same, the speed slows down, and the wavelength changes too. The average speed of light is less in glass. Now here you've got to be a little careful about when you read this. They're actually comparing air to glass here. So the speed of light is less in glass than it is in air, but it's slightly less in air than it is in vacuum. But it's just a tiny amount. So glass is probably the best answer. Most things around us are opaque. They absorb light without re-emitting it. Good examples of that: books, desks, chairs, the floor, the ceiling, unless you have a glass ceiling, and you. And what's going on in there, the vibrations given by lights to their atoms and molecules are turned into random kinetic energy and thermal energy. And you can notice this: you put something out in the sunlight, it usually gets warmer. These materials then will become slightly warmer. Now, metals are sort of a special object. Remember that they have free electrons that are able to move readily. That's the reason they conduct electricity and heat. So what happens when light hits a metal, it forces the free electrons in the metal into vibrations, and that re-emits the light as a reflection. So metals look shiny because of the free electrons, and that's also the reason they conduct electricity and heat so readily. Light in dry surfaces will bounce directly to your eye, but when a surface becomes wet, there's a thin film of liquid covering the surface. And that will basically let the light bounce around in that thin film of liquid, and that absorbs energy with each bounce. So the light becomes less intense, and it makes the wet surface look darker than the dry surface does. And that can also get very confusing when you're driving at night on wet roads, because you can get a lot of reflections and weird things don't look quite right when you drive on wet pavement. What is a shadow? Well, it's basically a blockage of light. A thin beam of light is often called a ray. When we stand in the sunlight, some of the light is stopped while the other rays continue in a straight line path. This is called casting a shadow. A shadow is a region where light rays do not reach. Now, there's two basic types of shadow. There's the umbral shadow, which is the dark type, and then there's the penumbral shadow, which is sort of a lighter gray shadow. Either a large faraway light source or a small nearby light source will produce a sharp shadow. A large nearby light source produces a somewhat blurry shadow. You can demonstrate this for yourself. All you need is a desk lamp and a table. The desk lamp on the table, turn it on. Hold your hand under the desk lamp in the light. If you move your hand, hold your hand far away from the table, the shadow that you cast on the table is rather blurry. As you move your hand closer and closer, you'll notice that the center part of the shadow gets darker, while the edges remain faint and blurry and light gray. The center part is the umbral part of the shadow. The light gray part is the penumbral part of the shadow. If you move your hand very close to the table, the penumbral part pretty much disappears and the umbral part takes over. So there's usually a dark part on the inside and a lighter part around the edges of a shadow. The total dark part of the shadow is called the umbra. The partial or lighter part of the shadow is called the penumbra. A penumbra appears where some of the light is blocked, but where the other light fills it in. Of course, that's this part right here. That's from an object that's far away. A penumbra also occurs where light from a broad source is only partially blocked. As the source gets closer and closer to the wall here, notice that this shadow gets less and less fuzzy and more distinct and more dark. Now, this can also happen in a solar or lunar eclipse. So the sun is large, and the rays will taper to provide an umbra, which is a total eclipse, and a surrounding penumbra, which is a partial eclipse. In a lunar eclipse, this is a lunar eclipse right here, the moon will pass completely into the shadow of the Earth, and when it does, it is experiencing a penumbra or total eclipse. In a solar eclipse, this is a solar eclipse. The solar eclipse, the moon casts a shadow on the Earth. In a lunar eclipse, the Earth casts a shadow on the moon. So in a solar eclipse, you have the sun, the moon, and then the earth in that order. In a lunar eclipse, you have the sun, the earth, and the moon in that order. Here's the anatomy of a lunar eclipse, and by no means are any of these drawings to scale. All right, so the earth casts a relatively large shadow because it's about 4 times the size of the moon. In a lunar eclipse, the moon, which is in orbit around the earth, will pass into the earth's shadow. There's 2 parts of the earth's shadow. There is the penumbra shadow, which is the faint, fuzzy stuff around the outside. That's this right here. And the umbra shadow, which is the darker central region. Orbits are not perfectly aligned here. And if they aren't perfectly aligned, then you can have a partial eclipse or penumbral eclipse. And you can barely even notice this. This one, the umbral eclipse, is really cool. If you ever get a chance to see one of these, please do it. When the moon passes into the umbral part of the Earth's shadow, it really experiences a total eclipse. And it's really neat. It can turn all these funky colors. Again, not drawn to scale. The sun, the earth, and the moon. This is a lunar eclipse. A total lunar eclipse can only occur at a full moon when the earth will block the sunlight normally reflected by the moon. But the earth has an atmosphere. An atmosphere is a transparent material. A transparent material slows down the light that goes through it. Anytime you slow light down, it can be bent. That's called refracted. The sunlight that grazes the edge of the earth passes through the earth's atmosphere and will be bent a little bit toward the moon. And what happens is that, of course, is the edge between the daylight and night. That is the sunrise or sunset. And so what you're looking at is that light from sunrise and sunset. You ever notice the sunrise and sunset is red? Well, our atmosphere will scatter blue light, which is what makes the sky blue. That blue light that we see of the sky is the scattered sunlight, scattered by the atmosphere itself. If you scatter the blue light, the remaining light is red. That's why sunsets and sunrises are red. And this red light that grazes this atmosphere, goes through the atmosphere and gets bent toward the moon, bounces off the moon, and we get to see it on Earth. So when you look at a total lunar eclipse, you're looking at the light from all the sunrises and all the sunsets on the earth reflecting off the moon to your eyes. So that's the only way you can see all the sunrises and sunsets at the same time. It also gives the moon that coppery glow when it passes into the earth's shadow. Here's a time lapse of a lunar eclipse. I've seen these, they're all different kinds of color. They can vary from just sort of a yellowish tan color to blood red to orange to brown to something the color of tapioca. They're pretty cool. I love these things. Here's another picture of one of these. I've seen one like this too. It's really cool. And that's all the reflected sunrises and sunsets off the earth, from the earth, bouncing off the moon at the same time. Now, solar eclipses can be either total, partial, or annular. And that will depend upon the alignment of the sun, the earth, and the moon. Okay, so here's a solar eclipse. The solar eclipse occurs when the moon casts a shadow on the earth. In other words, the moon passes between the sun and the earth. The moon is much smaller than the earth, so the shadow it casts is very tiny compared to the earth's shadow. So only a very small amount of people can see a solar eclipse, and it only lasts a very short time. And what's going on here is the moon is casting a shadow on the earth. Here from space is a picture of that shadow. Anybody who's in this part right here, that's the umbra, will see a total solar eclipse. Anybody who's here, outside here, that faint fuzzy stuff is seeing a partial solar eclipse. That's the penumbral part of the shadow. Here's a time-lapse photograph of a total solar eclipse. And you can see what happens when you get a truly total solar eclipse. The disk of the moon covers the disk of the sun, the visible part of the sun that's called the photosphere. The sun has an atmosphere called the corona. It's made up of plasma. That's the only time that we can actually see that from the earth, unless we make an artificial eclipse by blocking this out in a telescope. Why do we get annular eclipses? Well, it turns out that the orbit of the moon and the orbit of the earth are not perfect circles. They're elliptical. So the distance between the earth and the moon and the distance between the earth and the sun varies, depending on what part of the ellipse it's in. And when you look at something that's close up, it looks larger. That is, it covers a larger angular size than it is when it's further away and it looks smaller, which is a smaller angular size. The moon, when it's closest to the earth, has this angular size. When it's furthest away in comparison, it will be this angular size. The sun also has that same thing. When it's closest to the earth, it has a large angular size. When it's further away, it has a small angular size. Now, you want the disk of the moon to cover the disk of the sun to get a total eclipse. So what you really want to have is have the closest moon at the same time you have the furthest sun. If instead you have the sun closest when the moon is furthest away, the moon's angular size is not large enough so that its disk cover the disk of the sun. Then you get an annular solar eclipse. What's that look like? Instead of this, where you have the disk of the moon covering the disk of the sun and all you see is corona, instead you actually, the face of the sun peeps around the edges here, makes like a ring, and that is why it's called annular. Annular stands for ring. Now, light is the only thing we can see with our most remarkable optical instrument, the eye. As light enters the eye, it moves through a transparent cover called the cornea, which does about 70% of the necessary focusing or bending of the light before it passes through an opening called the iris. The iris is the colored part of your eye. So if you've got blue eyes, that's the blue part. If you've got brown eyes, it's the brown part. If you've got green eyes, it's the green part. That opening is called a pupil, and that pupil can expand or contract in response to the light to protect the eye from having too much light, or to open the eye in places of dim light to let you see better. The light will then, after it goes through this pupil, will then reach the crystalline lens, which fine-tunes the focusing of light that will pass through the gelatinous humor, which is in here, called the vitreous humor. It's a gelatinous fluid. And then eventually, the light will then pass to the retina. Light then passes to the retina, which covers the back 2/3 of the inside of the eyeball and is responsible for the wide field of vision that we experience. So it's on the inside of the eyeball. And the fact that it covers this whole part here is responsible for the wide field of vision that we experience. For clear vision, the light must focus directly on the retina. Now, the retina itself is not uniform. In the middle is the macula. There's a small depression. In the center is the fovea. The fovea is the region of the most distinct vision, and that's where the light from the lens wants to be focused. Behind the retina is the optic nerve. The optic nerve transmits signals from the photoreceptor cells to the brain. The photoreceptor cells are like little antennas that change the light energy into electrical signals in the optic nerve. There's also a spot in the retina where optic nerves are connected, and that's called the blind spot. It's called the blind spot because there aren't any light sensing cells in that spot. Now, the retina is composed of tiny antennae that resonate to the incoming light. Those are the light sensing cells, and they're like little radio antennas or little electromagnetic antennas. The rods will handle the vision in low light. They predominate toward the periphery of the vision of the retina. So in other words, they didn't live out here in this part of the retina. The cones handle the color vision in detail. They are denser toward the fovea, where the light from the lens likes to focus. So there are our central vision or day vision. The rods are our peripheral vision and our night vision. There are 3 types of cones. They are the color vision. They're stimulated by the low, intermediate, and high frequencies of colors of light. Now, our vision is poor from the corner of our eyes, but we're very sensitive to anything moving there. It's also very sensitive to low light. It is our night vision. And the reason it's so sensitive to things moving, well, suppose you are out on the plains of Africa at night and you see something moving in the corner of your eye. It's probably something that's trying to sneak up on you and eat you. So they're there to protect us from things that go bump in the night and that move in the night. If you've ever been out late at night and you're out in your yard and you see something moving out of the corner of your eye and it kind of gives you movement, that kind of feeling, well, that's that protective mechanism. You can't see color, okay, but you can definitely see motion, and it's very sensitive to low light, which is exactly what you need for night viewing. Now, the brightest light that the human eye can perceive without damage is some 500 million times brighter than the dimmest light we can perceive. Now, this is great, but it causes a problem. Because if you get a sudden flash of bright light or a part of the visual field is brighter than the rest, it can overwhelm the rest. And this can be dangerous like you're driving at night. It's kind of like what happens when you get hit by headlights and suddenly you can't see. We have something that protects us from that called lateral inhibition. We don't perceive the actual differences in brightness. The brightest places in our visual field are prevented from outshining the rest, from oversaturating, taking over for the rest. This is a weird sort of thing like this. Doesn't this side look a lot darker than that side? Well, this is the true brightness. Okay, the brightness varies like this. Okay, so this is dark. Right here is very dark, relatively speaking, than it is right here. Okay, but they're both actually the same. They don't look the same, but these are both actually the same. But you can see this sharp, apparently sharp delineation of brightness. When you separate these two, by putting this in here, this looks about the same as that does. Even here, it looks about the same. That's because of this lateral inhibition. It protects us from having this overwhelm that, because a lot of times you have to be able to see not just the brightest stuff in your field of view, but remember that tiger that's sneaking up on you? The dim stuff might be extremely important. And maybe you're looking into a campfire. You want to still be able to see the tiger sneaking up on you when you're looking at a light. So that's there to protect us. This is kind of an optical illusion. Here's some more optical illusions for your enjoyment. This slant line is straight. You put a ruler on that, it's straight. But if you look at it, it looks like it's zigzaggy. These dashes are the same length as those dashes. You put a ruler on these, they'll be the same length as those. This one I really like. Move your eyes around in this, and you can see the black dots show up and the white dots disappear. The more you move around, the more black dots you see. And you can't count them because they're not really there. This one is a famous one. It's a matter of perspective. You can never build this in the shop because this central prong here does not exist. You look carefully, okay, this one is actually just a matter of the way they drew it. Now the hat is not taller than the brim is wide. You put a ruler on this and no, it isn't. It's just a trick of the eye. This one I don't quite get. What does this sign read? To me it says Paris in the spring. I don't know. Now these rows of tile, are they really crooked? Well, if you actually put a ruler on this, you'll find that they probably are not. This line is actually parallel to that one. And although it looks like it's fatter through here than it is there, that's just because of these side lines fooling the eye. Here it looks just the opposite. It looks like this is closer together than it is at the edge, but in reality, they're parallel. James Clerk Maxwell discovered that light is composed of electromagnetic waves. Which of these does not belong to the family of electromagnetic waves? It's sound. Now, the way I like to remind students of this is through the old saying, nobody can hear you scream in space. But, I always add this, they can sure see you scream in space. The reason for that is because sound requires a medium to travel through, like air. There's no air in space. So sound waves do not travel through space. But electromagnetic waves travel just fine through the vacuum of space. In fact, they travel through the vacuum of space better than they do through anything else. So they can see you scream in space because they see you through electromagnetic waves. They can't hear you scream in space because sound is not an electromagnetic wave and it does not travel through vacuum. The source of electromagnetic waves is vibrating electrons, actually any charge. Light is transmitted by vibrating electric fields, but the source of these are vibrating electric charges, most commonly electrons. The electromagnetic spectrum is the span of electromagnetic waves ranging from very low to very high frequencies. Which of the following occupies the smallest percentage of the electromagnetic spectrum? It is visible light. Which of these waves is a higher frequency than visible light? The only one out there for that is ultraviolet. Also, gamma rays and X-rays would also be higher frequency than visible light. As I said, remember, you can bring anything you handwrite with you to test. So you might want to copy one of those electromagnetic charts into your notes. Which of these waves is the longest in wavelength? You can also get this off the chart. If you look on the chart of all of these, radio waves are the longest ones, followed by microwaves, by the way. The frequency of vibrating electron that emits violet light is about twice the frequency of one that emits red light. There is a relationship between the speed of a wave, frequency of a wave, and the wavelength of the wave. The speed of the wave equals frequency times the wavelength. For visible light, or for any kind of electromagnetic radiation, especially in vacuum, the speed is c, 3 times 10 to the 8 meters per second. So there's an inverse relationship between frequency and wavelength. Now, the wavelength of red light is 700 nanometers. The wavelength of violet light is 400 nanometers. You take the frequency of the violet divided by the frequency of the red light, it's going to be proportional to the wavelength of the red light inversely. Remember, wavelength of red light divided by the wavelength of the violet light. Wavelength of red light is 700 nanometers. Wavelength of violet light is 400 nanometers. That is 7/4, and that's very close to 2. So the frequency of the violet light is going to be twice the frequency of the red light. The electrons in the atoms that make up glass have a natural frequency in the ultraviolet part of the spectrum. Visible light that shines on a pane of transparent glass produces a chain of absorptions and re-emissions through the glass. Strictly speaking, the light that shines on glass is not the same light that travels through and exits the other side. So the photon that shines on one side is going to get absorbed and re-emitted many times, and it'll be different than the one that comes out. In reality, they're both twins, but they're not the same photon. The slowing of light in transparent materials has to do with the time for the absorption or re-emission of the light. Light that does not pass freely through opaque materials converted into internal energy of the material, and of course you feel that the material gets warmer. If you leave anything out in the sun or under a heat lamp, what's it do? It gets warmer. The types of waves that are absorbed by glass are both infrared and ultraviolet. The color of light that best passes through violet glass is violet. Okay, obviously, you got to read this carefully. The sharper shadow that is cast by a small light source that is near the object. When a shadow of the moon falls on the Earth, we have a solar eclipse. Now, be careful with eclipses. When it's a total solar eclipse and the moon just completely covers the sun, so all you can see is that corona. You cannot see the photosphere of the sun. You can't see the surface of the sun. That's okay to look at, but I would never suggest that you do that. That shadow moves very quickly across the face of the Earth. And all you have to do is look at it a little too long or a little too soon. If you're looking at the surface of the sun, you're hurting your eyes. You should never ever stare at the sun or look at it through sunglasses, binoculars, a viewfinder, or telescope unless you know what you're doing. Please be very careful with this. Do not buy cheap filters off the internet, okay, unless you know what you're doing, because if you look at the sun, your cornea and lens are focusing the light on the most sensitive part of your retina, the fovea. That's your central vision, and you cannot tell when you're looking at the sun, your eyes, there's no pain sensors in your retina, so you can burn your eyes without even knowing it. And the next day you find out when you got this big blind spot in your eyes. So please don't look at the sun. It's not worth it. Your eyesight's much more precious than that. The type of eclipse in the view of most people on the Earth would be a lunar eclipse. Anybody on the nighttime side of the Earth can see a lunar eclipse, but only those in the relatively small shadow of the moon can view a solar eclipse. That's because the moon is much smaller than the Earth and therefore casts a much smaller shadow. Total solar eclipses would not be possible if the sun were appreciably larger or closer. If the sun were closer or larger, it would be bigger in the sky than the moon wouldn't be able to cover it and be no total eclipse. If, on the other hand, the sun were smaller in the sky than the moon, then solar eclipses would be longer in duration, and total solar eclipses would occur more often. The retina of a human eye is composed of all of these. Rod and cone-shaped receptors. It's sensitive to far peripheral objects if they move, and actually does some processing of information before it passes the information to the brain. So all of these is the correct answer. The main reason we aren't ordinarily aware of our blind spot is that we have two eyes. Each eye fills in the blind spot of the other, so we don't see our blind spot. Thank you.